Hello, and welcome to our tutorial video demonstrating the integration of the EyeLink eye tracker with BCI2000. In this video, we will provide all of the necessary details to set up your system properly, along with a rapid serial visual presentation experiment to measure a subject's response to novel stimuli. What is BCI2000? BCI2000 is an open-source, multi-purpose software for biosignal acquisition, processing, and feedback. In BCI2000, a wide variety of hardware devices have been implemented, allowing for seamless integration of recorded biosignals with various peripherals, including joysticks, inertial monitoring units, electrical stimulators, and more. Why record eye tracker data? An eye tracker can be a valuable addition to any electrophysiological experiment. With an eye tracker, you can be certain the subject is visually attending to the screen. You can also see when the subject blinks or has rapid eye movements, called saccades. Integrating an eye tracker into BCI2000 synchronizes it with the neurophysiological data that is being collected, allowing for real-time feedback and easy offline analysis. In this video, we are using the EyeLink 1000 Plus eye tracker, which, according to their website, is the world's most precise and accurate video-based eye tracker. It is customizable and has an extremely fast sampling rate of up to 2 kHz. Let's begin to look at how to integrate the EyeLink eye tracker into BCI2000. First, we will go through the physical setup of the system. Other than the computer you already have running the experiment with BCI2000, you will need a second computer that runs the EyeLink system. The computer running BCI2000 will be referred to as the display PC, while the EyeLink computer will be referred to as the host PC. We will start by connecting the blue Ethernet cord from the host PC port labeled Display PC Ethernet to the display PC. Then we will connect the black Ethernet cord from the host PC labeled EyeLink Camera to the eye tracker. Next, connect the monitors that you will be using. We will be using one monitor for the host PC and 2 for the display PC. Make sure everything is plugged in, including the infrared illuminators on the eye tracker. Position the eye tracker in front of the display monitor used in the experiment. The participant will use the screen, while the experimenter will use the EyeLink and BCI2000 monitors. To connect to the EyeLink eye tracker, the IP address of the display PC must be configured. In the settings, go to the Network and Internet menu. Click on the Ethernet tab, then go to Change Adapter Settings. Then go to the Ethernet's properties where Internet Protocol version 4 is listed. Change the IP address from automatic to 100.1.1.x, where x is an integer between 0 and 255. This integer cannot be equal to the EyeLink's IP address, which is usually 100.1.1.1. Then change the subnet mask to 255.255.255.0. After this is configured, BCI2000 should be able to connect to the host PC. You can test this by pinging the IP address of the host PC and seeing if there is a response. If not, verify the Ethernet connection. If the host PC's IP address was changed, the IP address can be viewed on the EyeLink display after exiting the setup. Once the system is set up properly, the EyeLink eye tracker needs to be calibrated. This can be done with or without BCI2000. In this video, we will show both. To calibrate the EyeLink system, open the EyeLink File Manager. If the EyeLink eye tracking program has already been started, you must select the Offline or Exit Setup button, then select Exit EyeLink. Next, select the Configuration button, followed by the Screen Settings button. Using BCI2000, you must configure the parameter experiment params. This parameter contains values that are specific to the experimental setup. Set use to 1 if you intend to use the parameter set in BCI2000, or to 0 if you want to ignore them. If it is 0, EyeLink will use the values that are in the EyeLink file manager. If you plan to use remote tracking mode, which requires target stickers instead of a head mount, set remote to 1, or if you are in any other mode, set remote to 0. In the EyeLink system under screen dimensions, enter the width and height of the screen in millimeters. In BCI2000, this is phys-x and phys-y. Under display resolution, enter the width and height in pixels. In BCI2000, this is window height and window width in the application tab. For eye to screen distance, measure the distance from your eyes to the bottom and top of the screen. In BCI2000, enter these values in eye to top and eye to bottom. This setting is not used for remote tracking mode. Under camera to screen distance, enter the screen distance as well as the type of lens. In BCI2000, enter the lens to screen distance in the lens to screen field. However, the lens type can only be set using the EyeLink software. Whenever the lens is changed, you must specify it in the EyeLink software. Since this doesn't happen often, BCI2000 can otherwise be used to calibrate the rest of the system as shown. Once the experimental parameters are measured and set, the gaze data needs to be calibrated to the screen. To calibrate the display monitor, you will need to download an application called Track from the SR Support Forum. Google SR Support Forum, then click on the first result. Then navigate down to the Downloads tab. This Downloads page is the last accessible page without having an account. However, an account is free to make. Register for an account and fill out the required information. Once this is done and your account is approved, select EyeLink Developers Kit/API, and then EyeLink Developers Kit/API downloads for Windows, Mac, and Linux. After this, download the correct EyeLink Developers Kit for your operating system. When prompted, select the compact installation to only download the essential features. When everything is completed, open the Start menu and you should see the application called Track under SR Research. Open the Track application and make sure the stimulus is shown on the display monitor. If you cannot see the stimulus on the display monitor, make that monitor the main monitor in your computer's display settings. Follow the steps to the calibration page, then press space or enter to start the calibration. You can also validate the calibration using this application, or also view the image of the eye to optimize the focus. Now that the EyeLink eye tracker is calibrated, we can finally run the experiment. In this experiment, we will be presenting random stimuli with the fixation boundary. To use the eye tracker in your experiment, you must enable it in your batch file with log eye tracker EyeLink = 1. You can also optionally specify which eye you are recording, and since we are recording the left eye, we can put left or 0. We will also be using the gaze monitor filter to visualize the gaze data with BCI2000 and to enforce the fixation point. Follow the steps in the gaze monitor filter wiki page to implement this filter. And now, here's the experiment. You can see real-time feedback of the eye gaze data and can even see when the gaze leaves the enforced fixation zone. As you can see, the gaze monitor filter can eliminate the need for a third monitor. By visualizing the gaze data on the BCI2000 monitor, there is no need for the EyeLink display monitor. Note that the BCI2000 gaze monitor filter does not include the image of the subject's eye, which can be helpful for focusing the lens. This problem can be overcome by using the track application. By combining the uses of the track application and the gaze monitor filter, experiments have no need for the feedback given by the host PC display. In this way, BCI2000 simplifies the experiment and the setup even further. The data recorded with BCI2000 can be inspected in MATLAB using the load BCI DAT function. Use this function to load the recorded signals, states, and parameters that were used to design the experiment. By inspecting the states, you should see that a variety of different states were recorded. The EyeLink eye tracker records data over a couple of different coordinate systems, imaged here. Gaze data is usually the most applicable, as the coordinates are stored in accordance with the screen resolution. In our example, this is 1920 by 1080. This is taken from the raw pupil data, which is a second coordinate system on a plane a known distance from the screen. And the third coordinate system is the head reference, where it is on a plane a fixed distance away from the pupil. The href data is best for deriving the pupil angles. The fourth coordinate system is pupil size, which has arbitrary units. The coordinate systems routinely record negative values, but BCI2000 states only record positive values. To encode negative numbers to the states, potentially negative numbers are written in signed magnitude representation. To convert the data back to signed values, some processing is needed. A simple MATLAB function is provided in the EyeLink documentation of the BCI2000 wiki page. Hopefully you are now familiar with the EyeLink eye tracker system. An EyeLink eye tracker can be added to any BCI2000 experiment you are running and can be easily analyzed post-experiment. More information can be found on the EyeLink BCI2000 wiki page. Thank you for watching our video.